Okay, and there's someone waiting to come in. Okay, that would be great if each day someone would give me a quick reminder, but when the official lecture is starting, you know, to make sure that it is recorded. So yes, this is being recorded right now. So now we use the base 10 system. I'm using I have an old iPad where I don't have the iPen, so my handwriting will look mostly like this. Nowadays we use base 10, but that didn't come into the Western world until the year 1202. Other cultures developed base systems, and some cultures didn't invent base systems. So we have, for instance, in Rome, you had Roman numerals. And the Roman numerals are just a terrible system of numbers. And the Romans didn't make any accomplishments in math. And part of that was that they just had a terrible number system. Having a good number system really comes in handy. Actually, the Greeks did not have a very good number system, you know, really not that different from Roman numerals. And the Greeks made a lot of progress in geometry, but not quite so much in algebra. So even though base 10 and base 10 was created in India and in the Arab worlds, and we often call them like the Hindu Arabic numerals, those all were happening somewhere, you know, somewhere around the year 1000. But the Babylonians, we have this evidence from, you know, like 1600 BC. They actually had a positional number system. So they made a positional number system in 1600 BC, but it didn't really get shared very much. And it took thousands of years for other cultures to reinvent it. So the Babylonians have a positional number system in 1600 BC, but the Egyptians don't, and the Greeks don't, and the Romans don't. And it's not until like 1000 AD that a positional number system reappears. It's a really powerful thing to have a positional number system, and it's too bad it didn't get passed on back when the Babylonians did it. The Babylonians used a base 60 system. Now, base 60 system still gets used. Here's like a riddle. When can that be true? You can type it in. That's right. In time, 1:59 plus 1 minute is 2 o'clock. Our time is divided into a base 60 system with 60 minutes in an hour and 60 seconds in a minute. And that is because the Babylonians did that, so we still do that to this day. So let's look at what first of all, we found the reason we know so much about Babylonian math is that we found all these clay tablets, because unlike the Egyptians who had like a papyrus, the Greeks they had these clay tablets that when they were wet, they had this little stylus that they would make a little wedge shape that kind of looked like that into the clay, and it survived for thousands of years. So we have all kinds of tablets hundreds of thousands of tablets. Most of them are things like the grocery lists and things like that. But some of them had math on them, and some of those tablets have really important math on them. So the number 1 was just this, which we're going to write as 01, and I'll explain why. We're not going to have to write this. They call it spells like cuneiform, but I've heard it pronounced various ways. So if they put 2 of them next to each other, that would be 2. And they would do this all the way up to the number 9. But then for the number 10, they take the same sort of wedge, but make it diagonal. So you might be thinking, well, that's the base 10 system, isn't it? But no, and then they could do things like put like 2 diagonal ones or 3 diagonal ones and 4 like upright ones. And that would be 34. Now I'm writing the numbers, so they can go all the way up to 59 with that. And I think I have, let's just take a look. Here you go. You can see here on the screen the numbers from 1 to 59 written in this, how the Babylonians did that. Now, we're not going to be using their notation, but sometimes we might need to look at a source document. So we want to be able to read it, but you're never going to have to write it in that way. Now, here's where the Babylonian number system gets kind of interesting. So 59, has 5 diagonals and 9 upright ones, but the number 60 looks just like the number 1. But the way we're going to write that is like this: 0, 1, 0, 0. So our positional number system, each of the way we're going to describe the Babylonians is the first place is going to be the 1s, and that can go all the way up to the number 59. And the second place is the 60s, and that can go all the way up to 59. So if I have the number that looks like this, 59, 59, that is 59 times 60 plus 59, or 3,599. Because if I have a 3-number system, this is the 1's place, this is the 60's place, and this would be the 60 squared equals 3,600. So that's the base 60 system. So somebody asked, Ben asked, why did they use that? Why not use base 10? It's clear they had a kind of idea that 10 was important because they made a separate symbol for it. And this like 34 has kind of looks like a base 10 situation here. Well, there's a benefit to base 60 that we'll get to in a little bit. I'm not going to say it just yet though, but that is coming in today's lesson. So if you saw, so the reason I put these, I write each digit as a 2-digit number, so that, if I don't do that, that would look confusing. Like, is that 10? Is that the number 10? Is it the number 60 with 2 different places? So if I just make sure, so that's 60, whereas 10 like that is 10. So I'm going to always make my places. In some books, they might put commas in between them, like 5, 12, 1. I don't do it that way. I like to write 05, 12, 01. That way there's just no ambiguity. Every place has 2 digits, but the biggest number that could be in the place is the number 59. Now, if you want to change a number from base 10, from base 60 to base 10, it's implied that it's base 60 if you see groups of 2 like this. I should say that having like a calculator handy, I mean, you're on a computer that's got a calculator handy, but does anyone want to type in this number that looks like 3,655, but it's not because it's a base 60 number? What would that number be in base 10? And that's right, it is 2,215. You would do 36 times 60, because that's the 60s place, plus 55 times 1, which is 2,215. Now, going in the opposite direction is a little bit harder. This 220 is not a base 60 number, it's a base 10 number. We could, if we wanted to, like write a little 60 down here to tell us it's base 60 and a little 10 there to say it's a base 10 number. We don't need to. The base 60 is going to always look like this with the numbers with the 2-digit groupings, and the base 10 number is not going to have that. So a good way to do this, 1s, 60s. Well, the next place is the 3600s. And since 220 is less than 3600, this is going to be a 2-digit number. So what you can do is figure out the 60s place by dividing 220 by 60. And it goes in 3 times. And that's why we put the 3 there. And the remainder, that should be 40. The remainder, when the remainder is less than 60, that's going to be the 1s place. So 220 can be, in base 60, is 0340. Now, when the number is larger, like 8,150, there's a little bit of a shortcut. Well, first I'll show you what not that the long way takes that long. The long way would be to realize that 8150 is bigger than 3600, so I can see how many 3600s go into 8150, which is 2. And the 2 goes in the 3600s place. Then we could take the 950 and break that up into 60s. And you can see that that has 15 60s. And then finally, the remainder, when it's under 60, would end up being the 1s place. That's a fine way to do this. But I did want to show you an alternate, and I'll do it on a new page. I think I'll try to save these notes also. I'm gonna go back here for the 8150, and this whole thing's being recorded anyway, but I kind of like this. This is kind of interesting. Instead of dividing by 3600, what if I divided the 8150 by 60? I get 1, 15, 3, and down to 0, 5, remainder 50. Now I take the 135. So this 50 is going to end up being the last place. The 135, well, we divide that by 60. And the remainder becomes the second to last place. And then finally divide the 20 by 60. Well, that's 0, remainder 20, and that 20. So the 3 remainders become, the recordings are going to be posted on the YouTube playlist. So there's a playlist already with 20 videos on it. Oh, somebody's waiting to come in. There's a playlist already that's got 20 videos on it. And I'm going to upload this video when it processes to that same playlist. And there's a link to it on the Google Classroom. So this method of just keep dividing by the base, it's not as obvious. See, this one's more obvious. This last one is more obvious why it works. You know, I'm looking for the 3600 place, so I find out how many 3600s. This one's a little bit mysterious, the way it works. When you divide the first number by 60, this 135 includes all the 60s and the 3600s are all kind of grouped together in there. But the remainder is what will be left over after I took out everything. Now this 135, it's really not so obvious what that represents. But what that represents is if I had this 8150 broken up into groups of 3600, 60, and 1, and I divided by 60, the groups of 3600 would turn into groups of 60, and the groups of 60 would turn into groups of 1, and this 50 is not part of the process anymore. So they'd basically just be 135 things now, but each thing would now actually represent 60 things from the original, and it's kind of like that. It's actually pretty confusing why this keep dividing by the base method works. I personally prefer this method. Now I should mention that nowadays, you know, we know that 60 is 0100, and just 01 by itself is 1. Back in those days, they didn't have, as they say, a 0, a placeholder. So the number 1 and the number 60 would both be represented by the same symbol. Which is pretty confusing. But if someone said, my grandmother, you know, is this age, you would know from the context that they were 60 and not 1-year-olds. But it wasn't until a lot later that the idea of the placeholder for the 0 came about. So it was, you know, it was confusing. Sometimes I see like a larger, they had like another stylus for the 60, like a bigger one. So you can tell the difference between these two things, but not always. Now, why they use base 60 instead of base 10 will become more clear when we look at if you see this semicolon, that number is kind of like the decimal point in modern math. So this is not 12 times 60 plus 30. This is not 750. So 1230 would be 750. But semicolon 1230 is not. And I want to type in what you suspect. What are the, in base 10, 0.53, the 5 is the 1/10, and the 3 is the hundredths. What are the decimal places that is actually called sexagesimal when it's base 60? What are they each worth? And it's true, they are the 6. So the 12, this is the 1/60th place. And this is the 1/3600th place. So that's pretty precise to have a place that's so small. I mean, hundredths we can kind of picture because pennies or something like that. But yes, their second sexagesimal place was the 3600ths. So this number is 12 over 60. Which, if I reduce these fractions, it's 1/5 plus 1 over 120. And if I get a common denominator, I would end up with, I multiply by 20, by 24. End up with 25 over 120, which can actually be reduced now if I divide both things by 5. I get 5 over 24. So this is how they would represent the fraction 5 over 24. So they had basically like a decimal system. They didn't have fractions. They only had this, but in their mind, they would think of this the way we picture 5 over 24. A very sort of a famous fraction, 730 is 7 over 60 plus 30 over 3600. I personally like to reduce the fractions and then get a common denominator. And what is that thing reduced to? And it does 1/8. So this is their way of representing the number 1/8. And I just say, 730. Now, if you think about time, 60 minutes is in an hour. 15 minutes is a fourth of an hour. And half of that is 7 minutes, 30 seconds, is an eighth of an hour. So the idea of the 730 being 1/8 is not totally unfamiliar to us. Now, 1/8 in decimals numbers is 0.125, but in base 60, it's 730. And let's look at what happens in going in the other direction. What would 1/2 be in base 60? And that's right, it would be this 0.30, because 30/60ths is the same thing as 1/2. And 1/4 would be 15. 15 over 15/60ths is 1/4. And 1/5 would be 12. 1/5 of an hour is 12 minutes. And we've already seen that 1/8 requires a second, second place, 0730. Well, 1/2, 1/4, 1/5, 1/8, those are numbers that you could write in base 10 also. I want to see the previous slide. The previous slide, I was just showing how 730, to turn that into a fraction, you would do 7 over 60 plus 30 over 3600. So at this point, base 60 seems like kind of interesting, but not like, it seems like, well, it's not better than base 10. Obviously, we're so used to base 10, we feel like base 10 is like the more refined one and somehow, better because it came later. But there is something you can do in base 60 that you can't do in base 10. Or there's something. In what way could base 60 be easier to use than base 10? Anyone have any thoughts on that they want to type into the chat? Well, yeah, it's true that nowadays in astronomy we use base 60. We separate because degrees are also 360 degrees in a circle and 60 minutes in a degree and 60 seconds in a minute. So we use base 60, although we could use base 10 for astronomy pretty well also. But there is something about base 60 that is superior to base 10. And this would also be true about base 12 is a little better than base 10 for something. It has to do with, I wrote these 4 fractions because those are the 4 fractions that terminate in base 10. But most fractions don't terminate in base 10. And I see here it's divisible by 3. And that's right, because 1/3 in base 60 is 20.20. 20/60ths is 1/3. But 1/3 in base 10 requires repeating decimal. And 1/6 is the same thing as 0.10 in base 60, but 1/6 would require repeating decimal for base 10. And even 1/9, which would require a repeating decimal for base 10, is 0640. In base 60. So because 60 is divisible by 2. It's 2 squared times 3 times 5. Because, by the way, you might hear from time to time, and the reason why I don't do so many live classes is because I'm taking care of 2 children simultaneously. And you might hear some kids screaming stop in the background from time to time. And I might, if I mute myself from time to time, it's because I'm taking care of what's going on at home. You might have kids at home right now yourself that you're trying to listen to a lesson and do it. So we're all doing best that we're able to. That's why, well, some people, they're coming soon. 1/9. Most people wouldn't know that 1/9 of an hour is exactly 6 hours and 40 minutes. So that answers, this I hope answers the question of why, see, 10 is just 2 times 5, and the things that terminate, the decimals that terminate in base 10 have to have denominators that have only 2s and 5, 1/10 also. If the denominator in base 10 has any factor besides 2s and 5s, it will be a repeating decimal. But because of this 3 here in base, you see 12 would be okay, but then you wouldn't be able to get 1/5 as a terminating decimal. Now 30 would be pretty good. 30 is 2 times 3 times 5. I'm not exactly sure why they picked base 60 over base 30. Because base 30 would be, oh, so yeah, so we have our 10 fingers. Well, it seems like, and there's like way ancient cultures that use a sort of base 10 system, just like taking 10 sticks and tying them up. So you can see in the way they actually write their numerals, with a sort of like a base 10 thing going on. But then maybe when they started inventing their decimals, they realized that 10, wasn't good enough. Now they needed to have 30 at least to get that 3 to be able to do 1/3. But it looks like they somehow, I haven't seen evidence of a base 30 system. I've seen cultures that have base 20 systems, but I'm not sure when they made the leap, what's so special about 60. I mean, I've seen speculation. They knew that the year was approximately 360 days. But they knew it wasn't exactly 360 days. They would have known that it was 365 days, but maybe they thought that was some kind of, the 360 was pretty close to 365, and there is some speculation that some cultures would have thought that 360 was like an important number, and it is 60 times 60. But no, I'm not sure. There's no like, there's these tablets that have calculations, but there's no like narratives of, if they find a tablet that has someone using base 30 that's like from an earlier era, then they can say, oh, they must have evolved their system. But I'm not sure why I know 60 is nice, a nicer number than 10 as far as the base goes, but 30 is just as good. So we're not really sure. It's pretty amazing that we still use the base 60 system for time. Incidentally, they did try in the 1800s to redefine the second and the minute so that there would be 100 seconds in a minute, 100 minutes in an hour, that sort of thing. But it didn't, just like the metric system almost didn't catch on, metric time did not catch on. Okay, now I want to show you how, so here I have this 0640, and you might wonder, like, how would I get that? How would I calculate it? So I'll show you how that works. To change a fraction into a base 60 sexagesimal, I'll just call it a decimal. What you do is you set up a proportion. And when you solve this, 60 equals 9x, divide both sides by 9. You end up with 6 and 6/9. The 6 ends up becoming the first place. But this 6/9, what we do with that is we set up another proportion with a 60 here, the same base. And I personally like to reduce the fraction. And then you can see that y becomes 40. And 40's the other place. So it's pretty easy to change fractions. It's a little confusing about like, why is there a 60 here and not a 3600? Well, this means that it was 6 and 6/9 and 6, I'm gonna write 6 2/3 60ths. So that's like 6 60ths plus 2/3 60ths. That's kind of related to why that to why that works. Now, that look pretty good. We're about halfway through. Now, these reciprocals, they would actually take number. So this chart here of these reciprocals, 1/2, 1/4, and all that. Well, those they would put together into a tablet, and I'm going to come and show you. You have this in your. Let me bring the website back up. So if you go to like to the classwork for today, Babylonian arithmetic, and I'm going to try to do this each day, collect everything onto one document. And it is a document that if you have a printer, I think is worth like printing out so that during the class, you can refer to it. You can see the homework, in addition to the Delta math assignment, has you converting and fractions and all that. But here I have these two tables. Now in base 60, in base 10, a nice thing about base 10 is that the times tables just have 100 elements on them. And you could memorize, and half of them are repeated because of the commutative property. So you don't have to memorize that much to do the times table. Then the 1 times tables are real easy and the 10 times tables are real easy. So there's maybe like 40 facts that we have to memorize for the times tables. But in a base 60 system, to do multiplication and division, you would actually have to, your times tables would have 3,600 elements in it. So that's pretty hard. So instead, they would have books basically or on these tablets. So if you take a look over here on the screen, I'm going to zoom in on this a bit if I'm able to. One thing they would have is a times table like this. This is specifically for, they would have 59 of these. And this is just one of these. This is like a times table for, it's the 23 times tables in base 60. And look at how it goes. They have up to 9. 23 times 9 is 327 in base 60. Then they jump, well, they go to 10, but then they jump to 20, 30, 40, 50. And that's all they would need. And they would have 59 of these. Like, you'd have to have a 59 tablet thing. This is just one of them. So let me show you how you use this for multiplication. So if I have to do 23 times 57, let me I'm going to go back to the iPad. You could bring up that, that 23 times tables on your screen also to follow along. So the way I would do 23 times 57 with this times table that has 1 through 10 and 20, 30, 40, and 50, I would think of it, or this is what they would do, they would think of it as 23 times 50 plus 23 times 7, which is really just what we do nowadays when you like do 23 times 57 and you do our modern, multiplication process. You do a similar thing. But then they would look up on the table the 23 times 50, which I have the table on my screen, but you can't see it, is 1910. Oops, sometimes this iPad freezes for a second, and then a bunch of stuff appears at once. So 23 times 50 is 1910. Yeah, that equals something in base 10, but it's not important what it is. We want our answer in base 60 anyway. And according to the table, 23 times 7 is 241, which is 161. Then you add these two things together. 10 plus 41 is 51. 19 plus 2 is 21. And that's the answer. It happens to be 1,311 if you're wondering, what is that in base 10? But this table allows us to do it pretty well. Now, would you take a minute and try to do 23 times 24 with this method? You're going to run into a complication that we can talk about. I'm going to mute myself and give you like a minute. And you could discuss what the complication is in the chat. Okay, good. I see some of the type of discussion that I was hoping for. We have the 23 times 20. Oops, get ready for a little blob to appear. The 23 times 20 is 0740. And the 23 times 4 is 0132. When you add these things, we get 72. But just like in base 10, when you're adding like 15 plus 18, and you get 13 here, and you carry the 1. Well, remember, 72 isn't really 72 in their world. 72 is 0112. So we carry the 1, and what goes here is the 12. So there is like carrying in their arithmetic, but it's base 60 carrying. So this place can't go. If this place gets bigger than 60, you put it minus 60 in the 1's place and carry the 1. Now, I certainly permit you to write the number 72 here first, kind of like in your mind, and then think, oh, but that 72 is too big, so I'm going to carry the 1. Or if you want, you don't need to write it, but I'll allow you to kind of like mix, throw a little base 10 in there, even though the Babylonians would never do that. If in your as long as you get this 0912 as your answer, I'm happy with that. You don't have to like completely immerse yourself into the Babylonian way of thought and be like, what is this 72 thing? You know, as long as you get the answer at the end, it's okay if in your mind you're kind of translating it. Oh. Oops. Here you go. Thanks. When I slide the window, you don't see it. I didn't realize that. Okay, so that's adding. And the same thing happens with subtracting, you know, 05, 20 minus 01, 40. Just like if you're doing 52 minus 14, and you have to take away 1 from the 5 and kind of give it to the 2 to make it 12 and then subtract. Well, actually the same thing happens here. You can't do 20 minus 40, so you change this 5, you trade it, and this actually turns into, if you want to be real Babylonian, you would put an 01 there, just like we did here, and it's 0120. But personally, I go like that. Cheat a little bit, base 10. So you take 1 away from the 5, but you add 60 to the 20, and then you could subtract. And you've actually seen this in elementary school with time. You know, 5 hours and 20 minutes minus 1 hour and 40 minutes. And you would go like that. I remember that's something that they teach in elementary school. So it's not so different, but that's how borrowing works in subtraction for base 60. Okay, now, yes, and I'll even go like 1 foot 2 inches minus, or 5 foot 2 inches minus 1 foot 4 inches with like feet and inches. You know, you would go like this. You would borrow. You can't do 2 inches minus, so you'd trade one of the feet for 12 inches. So it's a similar idea for time, but you trade in one of the hours for 60 minutes. Well, that's what base 60 is. The base 60 time is the base 60 system. So if you find this number, if you're subtracting, and this number is smaller than this number, you take away 1 from the 60s place, and you add 60 to the 1's place. I think what's kind of confusing is that, you know, the Babylonians, whoops, was it, oh, sorry, 5, 3, 40. They would really do exactly what we do, but that 0120 to them is the number 80 in our mind. So then they would know 80 minus 40 is 40. But since we're in modern times, I would rather you go like this. It's like 5 hours and 20 minutes is the same thing as 4 hours and 80 minutes. And then you can subtract. So that's subtraction. Now, we did addition, we did subtraction, and before I get to division, I want to look at another way, because multiplication, that method of having 59 different times tables, that doesn't seem so practical. Well, if you go back to the document, which I'm going to bring up, I have a really handy, another chart. This thing, the table of squares. This is the squares of the numbers 1 through 50. It would be better to have them through 59, but I just don't have them all for some reason. So you can see 1 squared is 1, and 2 squared is 4, and 3 squared is 9. And when I get to 8 squared, it's 64, but it's written as 0104. This table of squares, you don't need, you just need it. You don't need 59 different times tables like this other thing. This one's only good for the number 23. This table of squares is good to do other stuff, and I'm going to teach you how to use the table of squares. And if you're on the Google Classroom, you want to bring the table of squares up on your computer, because I'm going to move it off of this shared screen in a minute. Or you can print it out. Probably have it open in 2 windows. Okay, here's how the table of squares gets used. Here's back to my iPad. Okay, so here's the iPad. The Babylonians had an algorithm based on the table of squares. And I would say if there's one thing that the Babylonians knew really well, oh, hold on a second. So if there's one thing the Babylonians, their greatest, most sophisticated mathematical accomplishment was being very aware that if you take something like, I'll do sort of like modern algebra, whoops. If you see these little squiggles, it's just the remnants of what happens when I try to get this. So they know that a plus b squared is not a squared plus b squared, but instead is a squared. Okay, they're really aware of that fact because they use it in several of their algorithms. They're also very aware that a plus b squared minus a minus b squared. Nowadays, we know that this is a squared plus 2ab plus b squared, and this a minus b squared is a squared minus 2ab plus b squared. And when you subtract them, almost everything cancels out except for the 4ab. This here, if I were to summarize what the Babylonians accomplished in math, this thing right here was their biggest accomplishment, because you'll see throughout the next 2 days, they utilize this identity a lot. You could actually rearrange this to say a plus b squared minus 4ab is equal to a minus b squared. That's a variation of it. And this is a highly important thing. Now, how did they figure that out? They didn't have like multiplying binomials the way we have today. Some people think that a picture like this is a really nice geometric interpretation of it. So we can see that the big square is composed of 5 things. 4 rectangles that are each AB. And see this guy in the middle? That square in the middle, because this is A and this piece is B, that's A minus B. So this picture tells us that A plus B squared minus 4AB is A minus B squared. And if you made it so A was exactly, if you made it so that A was exactly 2B, where have you ever seen that before? You can type it in to the chat. No, has anyone ever seen anything that looks like this? Maybe not in a math class. That should be something even more basic than that. It is something that's seen in tiles, like a bathroom floor. If you go to a restaurant, that's the most popular tile pattern. It's called the windmill tile pattern. I come to the browser. Windmill tile pattern. Okay, you can see all the different, you can see that there. Okay, well, let's see how they utilize this identity to do, let's say, 26 times 14. Here's their sneaky trick. They do 26 plus 14 squared minus 26 minus 14 squared, because that would equal 4 times 26 times 14. Remember, a plus b squared minus a minus b squared is 4ab. So then they divide that by 4. So that means it's 40 squared minus 12 squared over 4. Well, you go to the table of squares, and 40 squared in base 60 is 2640. And I don't know why, is it 12? Yeah. And 12 squared is 144, which is that. When you subtract 2640 minus 224, we get 16. We get 2416. But then we divide that by 4. Now, we haven't talked about division yet, but if each place individually is divisible by 4, you can just divide the places by 4 separately. You get 0604, which is the answer. And it's a direct consequence of, actually it's more of a direct consequence of this guy, that a plus b squared minus a minus b squared is 4ab. So if I subtract those two things, divide by 4, I'll end up with ab. Now you might wonder, what if I wasn't so lucky? What if these two things were not divisible by 4? I'll get to that in a bit. I want to show you a second algorithm they have. Another way to do it is to do 26 plus 14 squared. This last method requires 2 table lookups. You have to look up 40 squared and 12 squared. This other way requires looking up 40 squared, but then looking up 26 squared and 14 squared separately. So there's 3 lookups now. But this one we have to divide by 2 instead of 4. And that's because they know that a plus b squared minus a squared minus b squared is just 2ab. We can see that with this picture. So a plus b squared is this whole thing, and if I take away the a squared and the b squared, I'm left with just 2ab. So I can do the same question. It's 2640, 1116. I'll subtract those first, get 1514. Sorry, 1524, I mean, and then do 1524. The 14 squared is 0316. I'm glad I don't need to do any borrowing for this, get 1208. And the 1208 I can divide by 2. Since they're both even, I can do 0604. Same answer. That's 364. You might wonder what happens, how do I divide by 2 if I have like, let's say, I'll divide that by 2. Well, the trick for that is to change this, sorry, can I change it to a 7 just so we don't get. The trick for that is to change the 7 into 06, and then kind of like put a 60 there. And now, because this was odd to begin with, but by change, I know this 60 isn't you're not really allowed to put a 60 into that third place. But if I do it just temporarily, I now can divide everything by 2. And same thing happens with dividing by 4. For this one, this 15 is not divisible by 4, but if I take away one thing, it would be 14, it's not divisible by 4. So I'd bring this all the way down to 12. And I'm gonna just, in my mind, that means I took 3 of these, so I'm gonna put 180 here again. And this 180 is like, they wouldn't actually do that because they didn't think of 180 in that way. But for our purposes, I think we can do this. And then we get 02, 03, 180 divided by 4 is 45. This number here will definitely be divisible by 4 because 60 is divisible by 4. So there's no chance I'm going to have to sort of do that again. I'm going to put parentheses around this 60. Again, that's not really what they would do. But in their mind, I think they were just good at knowing, oh, 7, half of that is 3.5, just like we know 3.5. But 3.5 for them is 330. So that's kind of, and same thing with this. We might say 15 divided by 4 is 3 and 3/4, but 3/4 is 75 in their world, and 1/4. 3/4 isn't 75 in their world. 3/4 is 45 in their world, and 1/4 is 15 in their world, and 1/2 is 30 in their world. So if they have these like 3 facts kind of at their fingertips, they wouldn't struggle with knowing that 7 became 330, or even that 15 divided by 4 is 3 3/4. So those are just some ways to think about it. Okay, now there's only one thing left for today. If you're dividing by some other number, maybe I should also show you that if you're doing like a real complicated multiplication, like 2017 times 7, they can use sort of like a modern approach, just like you do multiplication now, but it gets a little complicated with the carrying and all. The way I would do this, I would do 17 times 7, which is, using some times table or something, is 0159. I permit you to do that on a calculator. Just do 17 times 7 on my calculator here. 17 times 7 is 119. And 119 is less than 120, so it's 0159. Then, to do 20 times 07, I'm going to put 2 zeros here because it's not 20, it's 2000 times 07. So that's where these come from. Just like when you do sort of like, if I were to do like 25 times 3, and I don't want to do it all in one line, I would do 5 times 3 is 15, and 20 times 3 by putting a 0 here would be 60, and then add them together. So that's how I'm doing this also. So 20 times 7 on my calculator, I know, or 2 times, 20 times 7 is 140, which is 120. 120 plus 20. But this really isn't 20. It's 20 times 60, but that's okay because these 2 zeros take care of that. Multiplying by 60, you just shift everything over. So it becomes like this, 2002. And then when you add them together, you get 02, 2159. What is that? Doesn't really matter. That's what the answer is. What is that in base 10? Since we're asking for the answer in base 60, that's the answer in base 60. Anyway, as you do these questions, you want to write this stuff, but if on the side you're like doing 17 times 7 is 119, and then you're converting it into 159, that's perfectly fine. You're not going to be going, 17 times 7 is 0159. That's just not how we think of it. this is not the second table of square method. So the two table of square methods are, the first one was a plus b squared minus a minus b squared over 4. And the second one was a plus b squared minus a squared minus b squared over 2. Those are the table of square methods. This other question I was showing you was like a more involved multiplication with larger numbers. I probably should have done that before showing you the table of squares method. Okay, the final thing that I want to show you is how they did division. Yes, we've seen dividing by 2 and 4. Those are, easier. But general division, for that, they would utilize the reciprocal table. And I actually have, let me bring up, in the Google in the Google Classroom, in this document here, I have this thing you can see. And it has reciprocals for 1/2, 1/3, 1/4, 1/5, 1/6, 1/8, 1/9, 1/10. But they actually keep going to 1/12, 1/15, 1/16, 1/18, 1/20, 1/24, all the way down to 1/50. So these, notice how they do it with a comma in between. So I'd write this as 0115, but they do it with the commas. So the way they divide, come back to the iPad. This is our last question for today. The way that they would divide 1835 divided by 5 is instead they would multiply, because 1/5 is 0.12 in their world. And then they would multiply 1835, 12. Just like we do nowadays, you could ignore the decimal point and take care of it at the end. So what I would do, if I was doing this now, I would say 35 times 12 is 420 in modern. But 420 is 7 times 60. Then I would put 2 zeros here because I'm going to do 18 times 12, but it's not really 18 times 12. It's 18 times 60 times 12, but that's okay. It gets the same answer as whatever 18 times 12 is. On my calculator, I just say 18 times 12 in base 10. And I see that's 216. 216 is bigger than 180. 180 is 03, so it's 0336. And now I can add together those two numbers, 00, 43, 03. But remember, there was this decimal here, so that would go over there. And the answer is 343, which is 180 plus 43, which is 223. And you could check that 1835, which is some large number, 18 times 60 plus 35, that's 1,115 divided by 5. 1115, just to check that it's right, is 223. So just so you know, that is 1,115 divided by 5, which is 223 in base 10. Well, it works. It got 0343. Okay, everybody. So that was today's lesson. Now, I don't know how many of these I'll do. I'm going to try to do this week just to get us like used to me and the way I teach, so that watching videos, I'm also going to try to make this chat room like anyone could go on at any time and just type stuff and ask stuff, and I'll go to it several times a day and other people will go to it. Definitely going to want to make a sort of community, an effort where people are communicating with each other, and since we don't have the live class to do that. Okay, does anyone have, so for homework, you have the questions on that Babylonian arithmetic sheet. Plus, if you go to the Google, to the Delta Math, register for the one for math teachers, and there's like 10 questions to do. They're just converting from base 60 to base 10 and base 60 to base 10 to base 60, not even using decimals or anything. Yes, the Google Classroom. The best thing for me would be a PDF, meaning if you can download if you get the Cam Scanner app, I think it's a free app. You know, they charge you for storage if you run out eventually. It allows you to take like a nice picture, like a multiple page picture that's a PDF, and it straightens it out. So if you take it at an angle, it turns it into a nice rectangle. Dropbox also has it. That's free. But I would love to have rather than individual pictures, because maybe your homework's 5 pages or something. If you can take, if you can make it one PDF document, that's a lot easier for me. By the way, the way I receive it, it's really difficult when it's on like 10 JPEGs. So if you're able to make it one PDF document. For Delta, do the math majors. I know I had written the wrong thing at first. See if you can change it. If not, I will, you might sign up for both, and I'll remove you from one if it doesn't let you. Okay, now let me take a quick, almost like an attendance, because I have 10 people here. Let me just do a quick screenshot of today's class. Okay, great. Okay, everybody, I'll stick around for a couple of minutes right now. If anyone has questions, you can stay on and use the chat. If you don't want to listen, you know, if you just want to chat with people about some of these things right now, you can watch me talk to some other people. I am going to try to put up a Google Hangout for the class, try to get that up and running today as a place also. You update through, when you click on the document, when you click on the assignment, there's a thing for like attach, and you can attach a, you don't actually change the Google document. You attach a document that you make, which is ideally like a handwritten scan, a single file that has a scan of all the pages that you did as a PDF. Okay, everyone, well, you're dismissed for today. And if anyone wants to stick around, I'll bring my video up. And how do I stop the screen share? I know I'm on the screen, but I don't know how to make it so that. Oh, and I'll stop the recording now.